Graphs of basic functions. In this particular video, I try to discuss graphs of some very basic functions. Okay. Then we try to understand how to create new function graphs from old functions. And please don't misunderstand that we are going to draw a graph for every function in the world. We try to understand graphs of very basic functions. With the help of that, we try to create graphs of some other functions. We are not graph drawing tools, okay, to draw graph for every function. See, actually when you know graph of a function means you know more information about the function. See, if you know more information about the function, we can at least get the rough sketch of the graph. Okay, so at least to know rough sketch of the graph, the basic function graphs, and this ideas to create new functions from old functions will be useful. So in this video, I will be discussing the following concepts: graphs of basic functions, new functions from old function, that is we will be understanding this translation, that is also called shifting, stretch and compression properties, and reflection properties. Okay, so I start with the graphs of basic functions which we should know. The first one under this is constant function. See, we all know that x is equal to 0 means y axis, and similarly y is equal to 0 means x axis. Okay, now y is equal to c means it is parallel to x axis. So it is x axis parallel to x axis. That is a graph of the constant function y is equal to c. Okay, see, actually I given this particular graph using a graph drawing tool. Okay, but we should know at least this rough sketch of the graph. Okay, because it is possible, so I just done this. Okay, actually this particular example, if you see, it is y is equal to 3, it is passing through 3. Now one need to understand what is domain of the function and what is range also. Domain means for what values of x the function is defined, and range means what values the function can take. That is images, set of all images is what is called as range. So domain is, it is defined for all values of x, all real values of x. So domain is real number system. And what is range of this? It takes only, okay, here c means it takes only one value, that is c. Suppose y is equal to 3 means it takes only y is equal to 3. Got it? The next important function, identity function. What is a graph of identity function, sir? It is a line passing through the origin and making 45 degrees with positive x axis. Okay, so again using tool we can get a beautiful graph like this. But as I told you, at least this rough sketch we should get in your mind. Okay, the picture we should get in your mind. Whenever you see y is equal to x, immediately we should get that y is equal to x picture in your mind. Basic functions graphs one should know. Am I clear? Now if you see domain of this particular function, it is defined for all values of x, no restriction. Range, see here you see the graph is there above the x-axis and below the x-axis. That means it takes all values of y. That is, range is also R, real number system. The next one is square function. See, here I am writing rough diagram and perfect sketch using a tool. Am I clear? Like this. This is the graph of square function. And if you observe the domain, the entire real number system, that is all real values of x, the x square function is defined. But range is, see, there is no graph below the x-axis. That is, it takes only values of y from 0 to infinity. So the range is 0 to infinity. We call it as non-negative real numbers. What is it called? Non-negative real numbers. Actually, we can also write it as R plus union 0. See, different ways of representing range, sir. Okay, this 0 to infinity can be written like this or like this. Different ways we can express this. Is the idea clear? And one interesting fact here, we actually written graph for y is equal to x square. Actually, the graph of x power 4, y is equal to x power 4, y is equal to x power 6, all these fellows will look similar. Of course, similar means they are not same. There will be slight variation. For example, up to 1, suppose if you take y is equal to x power 4, the graph of y is equal to x power 4 up to 1 would be below this, and after 1 it would be above this, something like this. Okay, don't go with exact scale, sir. Something like this. If it is like this, then that would be something like this. Am I clear? So shape would be almost similar to that of parabolic. Am I clear? So x power 4, x power 6, all these fellows have similar graph. Okay, that is about square function. The next one is cube function. Okay, so the graph of y is equal to x cube is this. See, as I told you, we should know the rough sketch of the graph. That is what we need to remember. Okay, if you use a tool, you may get a beautiful diagram. See, don't worry about the beauty of the diagram, sir. The idea we should get, the picture. Am I clear? And domain, if you see, the entire real numbers. That is all real values of x, it is defined. Range also, you see the graph is above x-axis, below x-axis means range is also R for y is equal to x cube. And graph of x power 5, y is equal to x power 7, they are also similar to that of this one. Am I clear? So that is about cube function. The next important function is absolute function, mod x. The definition of mod x is like this: minus x for x less than 0 and plus x for x greater than or equal to 0. That means whatever x you give, it makes it positive. So obviously the range would be positive real values, or 0 also is there, no, therefore non-negative real values you can say. So the graph of mod x would be something like this. Okay, and rough diagram one should know. So domain and range. Domain means where it is defined for all real values of x. Range r plus union 0, or you can say from 0 to infinity. Okay, that is about absolute function. The most important one, exponential function. See, actually a power x is a general notation for exponential function. So the graph of y is equal to e power x is like this. Okay, actually because it is not to the scale, we just need to understand it will not touch the y-axis, this x-axis, it will be something like this. It will touch at infinity. Am I clear? Limiting case it will touch. So that would be the graph of y is equal to e power x. See, actually if you draw the 2 power x graph, so 2 power x graph also would be something like this. So it also will be something like this. And 3 power x graph, if you take it, it may be something like this. So it is 2 power x graph, it is 3 power x graph, and it is exponentially is a special case of that particular one. E power x. This is graph of this. Okay, they all pass through at x equal to 0, they are all 1, sir. Am I clear? So that is the idea. So this is the graph of e power x. So whenever you see, immediately you should get this picture in your mind. At x equal to 0, it is 1. So what is domain of this fellow? Domain is, it is defined for all real values of x. Range 0 to infinity. Actually it is only positive real numbers. So some people worry about 0 to be included. My dear friends, limit as x approaching minus infinity, e power x is 0. Of course we write e power minus infinity as 0 for brevity, but it is to be understood that it is only in the limiting case it tends to 0. E power x is never 0. E power x is never 0. So 0 not included. That comes only in the limiting case. So 0 to infinity. That is the range of e power x. Okay. The next one is logarithmic function. One important point is, actually logarithmic function we need to give the base of the function. What is the base? So in engineering mathematics course, mostly we are worried about logarithmic to the base e, natural logarithm we call it. So unless or until I explicitly mention, when I write log x means I mean log x to the base e, because even in some books they use this particular notation. It is just a convenient notation. But if you want to use strict notation, you can always use that ln x notation for log x to the base e. This is a correct notation. Or you can always write that base e also. So don't worry about that, base is not written like that. Okay. See, actually logarithmic function, log to the base e is inverse of e power x. So if you draw this, y is equal to x line. See, this is your e power x graph, right? So this is inverse of that. You already told how to get the inverse. You have to reflect about y is equal to x. So it is actually e power x graph, and this is log x to the base e graph. So it is reflection about y is equal to x. Okay, you need to draw this properly, sir. Like, Am I clear? So like that. Is the idea clear? So logarithmic function. Now the beauty about the logarithmic function is domain is, see, it is not defined for x less than 0 and x equal to 0. This is defined only from 0 to infinity. So you can also write it as x greater than 0, or you can also write it as r plus. Now what is range of this fellow? Range is, see, the graph is there from, see, actually if you see the graph, it goes something like this. Okay, it's like this. Graph is from minus infinity to plus infinity. So it is the entire R is range. Range is the entire real number system. Okay, so that is about logarithmic function. Is the idea clear? Now we try to see the famous trigonometric functions. Am I clear? The first one is sin x. The graph of sin x. Okay, so this is 0, this is pi, and this is 2 pi, and x equal to pi by 2, the graph is 1. See, actually if you draw this line, this particular line, straight line, sir, you have to draw it. This is actually y is equal to minus 1, and this is actually y is equal to plus 1. So if you see the domain of sin x, it is defined for all real values of x, but range, the sin x value lies between minus 1 to plus 1. Y, na, we are calling it as y. Y ranges from minus 1 to plus 1. Minus 1 to plus 1. That is the range of sin x. See, this is what the information one need to know about basic function, nothing more than that. The general picture of the graph, what is domain, what is range. That's it. Next one is cos x. The graph, see, at x equal to 0 it is 1, at x equal to pi by 2 it is 0, and again at x equal to pi it is minus 1, and 3 pi by 2, and again 2 pi, it goes at 1. So 0 to 2 pi, it's a periodic function. Sine, cos, these are periodic functions of period 2 pi. So the graph will be repeated at every interval of length 2 pi. Now here also you can see this, it is going from minus 1 to plus 1. Okay, please write the straight lines. What is domain of this? Domain is R, and what is range? Range is from minus 1 to plus 1. The cos x values lies between minus 1 to plus 1. We write like this, na, cos x lies between minus 1 to plus 1. That is about cos x. Then comes tan x. See, tan x fellow is having discontinuities at x equal to pi by 2. See, at x equal to pi by 2, left side what happens? As x approaching pi by 2, from left side it tends to plus infinity, and as x approaches pi by 2 from right side, it tends to minus infinity. See the graph. This is pi by 2, sir. From left side when you are approaching, the functional value is reaching plus infinity, and when x approaching pi by 2 from right side, the functional value is approaching minus infinity. So this is having discontinuity, we call it, at x equal to pi by 2. It's not defined at x equal to pi by 2. At x equal to pi by 2, it is not defined. Limiting case values are tending to plus infinity, minus infinity. Is it clear? So similarly, it is minus pi by 2 also, story is same. Okay, from left side when you are approaching, you are going to minus infinity. From right side when you are, from right side when you are approaching, you are going to minus infinity. From left side when you are approaching, you are going to plus infinity. So at pi by 2, minus pi by 2, 3 pi by 2, minus 3 pi by 2. So this is the story about tan function. So if you see domain for tan, you will have this particular problem at pi by 2, 2 pi by 2. So that is general 2n plus 1 pi by 2 you can write, where n is integer. That point you have to remove. See, actually what is tan x, sir? Tan x is sin x by cos x. So cos x should not be 0. Okay, let me just put this sin x and cos x. Sin x is 0. Sin x is 0 when x equal to n pi. The zeros of sin and cos are also very interesting. So let us put those values. Sin x is 0 when x equal to n pi. That is 0, pi, 2 pi, minus 2 pi, plus 3 pi, like that. All this. Similarly, cos fellow when you consider, Cos fellow, when you consider cos x is 0 when x is equal to 2n plus 1 pi by 2. N is integer. Okay. So this is additional information, zeros of the sine and cos, and that is exactly what we use for this tan x function. So tan x is not defined when cos x is 0. So cos x should not be 0. That is, x should not be equal to 2n plus 1 pi by 2. So that is what we removed. And again, if you want, you can find when tan x is 0. Tan x is 0 if and only if numerator is 0. Sin x is 0. That is, if and only if x equal to n. This is the information. But range of tan x, range domain is having difficulties at x equal to pi by 2, minus pi by 2, 3 pi by 2, minus 3 pi by 2, like that. What about range? Range, it is defined for, it takes all values from minus infinity to plus infinity. That is about range of tan x. Okay. Now the next function is cosecant x. Now what is cosecant x, sir? Cosecant x is 1 by sin x. Therefore, sin x should not be 0. That means x should not be equal to n pi. So it is not defined at 0, pi, minus pi, 2 pi, minus 3 pi, and so on. Okay, that is about cosecant x. So if you want to see domain for cosecant x, this n pi's we have to remove. R minus n pi. See, at 0 it is not defined, at pi it is not defined, at minus pi it is not defined. Am I clear? It will be having discontinuities, or the function is not defined. Okay, at n pi. Clear? Not discontinuities. We need not, when it is not defined, what is the question of continuity there? Okay, so it is not defined. Okay, you can also say discontinuities, that is secondary. Now what is range? So the range, if you observe, this is actually, if you draw this particular line and this particular line, this is y is equal to minus 1 and y is equal to plus 1. So the values are above 1 and below minus 1. So it is actually minus infinity to minus 1, minus infinity to minus 1, union plus 1 to infinity. It takes values above that, that is above 1. There is no graph from minus 1 to plus 1. So there is no range, that is, it will not take values from minus 1 to plus 1. Minus 1 to plus 1 is removed from R, like that also you can check. That is called range. Okay, about cosecant x. Next comes secant x. What is secant x, sir? Secant x is 1 by cos x. So cos x should not be 0. That is, x should not be equal to 2n plus 1 pi by 2. So if you want to know domain, remove all this 2n plus 1 pi by 2. So the graph of secant x would be like this. Okay. So what is domain for this secant x, sir? R minus 2n plus 1 pi by 2. So it will have discontinuity as at pi by 2. Not defined at pi by 2, minus pi by 2. There is nothing wrong if you say discontinuity, sir. Okay. So like that. Pi by 2, minus pi by 2, 3 pi by 2, minus 3 pi by 2, and so on. What about range? Same as cosecant. So R minus interval, minus 1 to plus 1. Or you can say minus infinity to minus 1, union 1 to infinity. That is range, the values which secant can take. Okay, this is about secant graph. The next one is cot x. Okay, what is cot x, sir? Cot x is, cos x by sin x. So sin x should not be 0. That means x should not be equal to n pi. So if you want to see domain for cot x, what is domain? R minus n pi you have to do. That is 0, pi, minus pi, 2 pi, minus 2 pi, and so on. Okay, the graph of cot x. See, it will be having problem at 0, pi by 2. Okay, 0, pi, not pi by 2, pi, sir. Pi, minus pi, It's not cot, I mean it's not tan, cot, na. So pi, 2 pi, minus 2 pi, and so on. At those points the function is not defined. And what about range? Range is no issue, it is defined for, I mean it takes all real values, minus infinity to plus infinity. So these are the informations about basic functions. Now we try to see some special functions. Square root function. What is square root function, sir? See, actually when you say y square is equal to x, what is inverse of this function? Y is equal to plus minus root x. But this is not inverse. Okay, because one fellow taking two values, it cannot be a function actually. But this will give you two functions separately. One is y is equal to root x is one function. Y is equal to minus root x is another function. Actually, y is equal to minus root x is this particular. This one. Here it is y is equal to root x. This fellow is having domain only from r plus union 0. That is x greater than or equal to 0. And range also r plus union 0. That is x greater than or equal to 0. Okay. But whereas for this fellow, minus y is equal to minus root x, domain would be r plus union 0, but range would be r minus union 0. This would be the range. It takes only negative and 0 values, right? This is the range. This is the domain. This is domain and this is the range. Am I clear? Like that. So that is about root x function. The next one is reciprocal function. Y is equal to 1 by root x. They also call it as rectangular hyperbola. So this particular graph, when x should not be 0, clearly we can understand this should be removed from domain. Domain will not contain 0, r minus 0. Okay. And what about range, sir? So it takes all values, sir. It takes all values, okay, except 0. So y also will not be 0, sir. So r minus 0 would be the range. So it is rectangular hyperbola. See, you know, general hyperbola graph, you know, right? This is hyperbola, but it's called rectangular hyperbola because in first and fourth quadrant you will find that hyperbola part. Okay, so it is also called, there is a special name, rectangular hyperbola. And this is a graph of this. Okay, like that. Okay, the next one is greatest integer function. Some people call it na GIF. They forget the original name of that greatest integer function. Okay, greatest integer function means greatest integer less than or equal to x. That is the meaning. See, actually if you say 2.71, is it integer? 2.71 is not integer. What is the greatest integer less than or equal to this? Like, suppose if it is say 3, is it integer? Yes. So what is greatest integer less than or equal to this? 3. Like, so if you take any value from 0 to 1, like 0 0.2, 0 0.3, what is greatest integer less than or equal to that? 0 only. So they'll take value 0 only. From 1 to 2, 1 also included, sir. 1 to 2, anything you take, you're going to get answer as 1. The functional value as 1. 2 to 3, 2 it is 2 and up to 3, 3 is not there. So when it is not there, now we put this circle like this. Okay. So it takes values 2. 3 to 4, it included. 3 to 4, it is not included. So it is 3. So at 4, it again becomes 4. Up to 5, like that. And again from minus 1 to 0, it takes minus 1 value. Like that. Here it is minus 1, here it is minus 2, minus 3. See, you see single steps. So that's why it is called step function. So if you see domain, it will have difficulties anywhere. It is where it is having value for everything. Na? So domain is the entire real number system. But range, it takes only integer values. See here 0, 1, 2, 3. So it takes only integer value, -3, -2, -1, 0, 1, 2, 3, takes only integer value. So this is about greatest integer function. The next one is fractional part function. See, actually when you are having suppose something like 2.71 fractional part function, it is 2.71 minus bracket function. See, greatest integer function can also be called as bracket function, okay, floor function, different names are there. So it is 2.71. So what happened, this greatest integer function, the fractional part will be removed, so it is 2. So what is that you are going to get is the fractional part you are going to get. So what happens, whatever fractional part is there, only that would be your answer. So for example, if it is 0.5, 0.5 will come, 1.5, 0.5 will come. So always from 0 to 1, the answer would be from 0 to 1 only. From 1 to 2, the answer would be 1 to 2 only. Okay, from -1 to 0 also the answer would be 0 to 1 only. Again 0 to 1. See, whatever is the answer is always from 0 to 1. Okay, it ranges from 0 to 1, 0 to 1. Okay, for example, if you are having say 3, so what is it, 3 minus 3, so what is it, it will become 0. At 3 it becomes 0, at 2 it becomes 0, like that. You are going to get this. So what will be domain of this particular function? Domain is the entire R, but range is, see, it never reaches 1, sir, it is 0 to 1. Here it will be having, the circle means at this value it will never reach. So 0 to 1. So this is called fractional part function. Okay. So previous one is greatest integer function. These are some special functions. Okay. So at least minimum function graphs one need to know. Okay. So I just quickly review the graphs. So we need to understand like this: y is equal to constant means parallel to x-axis. Y is equal to x means straight line passing through the origin. Y is equal to x square is parabola. Y is equal to x cube means the cubic function. Y is equal to e power x means the graph is this one. And y is equal to log x, the graph is this is the graph. Okay. Is the idea clear? And we are also having y is equal to root x. Root x function is this. Okay. And greatest integer function, okay, step function you can call it. Okay, it is step function, sir. Steps you will be having, steps like this. And fractional part function, just now we done it. What was the fractional part? It is always this the graph. And of course the sin x, cos x, sin x graph. What is the graph of sin x? This is the sin x graph. Okay, cos x graph, at x equal to 0 it is 1, so it is the graph of that. Am I clear? Tan x, so we will be having, this is the graph of tan x. Minimum graphs one need to get immediately whenever you think about basic functions. Now we try to understand new functions from old functions. New functions from old functions. By applying certain transformation to graphs of a given function, we can obtain graphs of certain related functions. So under this, we try to understand the following: translation, stretch and compression, and reflection. First, we try to see this translation, also known as shifting. So here we discuss vertical stretch, vertical shift and horizontal shift. See, whenever you add c to the function fx, suppose y is equal to fx is the original function, okay, and if you add c outside, okay, and c should be positive, okay, what happens, the graph will be shifted c units upwards, and when it is fx minus c, the same graph will be shifted c units downwards. This is called vertical shifting. And if you subtract c from the argument, that is fx minus c, the graph will be shifted c units right side, horizontal shift it is, and fx plus c, the same graph will be shifted c units left. When it is plus c, it is shifted c units left side. So the idea is something like this. Suppose your original graph is this fx graph, Okay, so what happens when it is fx plus c? The same graph shifts c units up. This is fx plus c. And if it is fx minus c, the same graph shifts c units down. Graph is same, c units downwards it will shift. Now suppose if it is fx minus c, okay, so the same graph shifts like this, it is fx minus c. See, for argument we are subtracting, from argument you are subtracting c, and same thing, suppose if it is fx plus c, f of x plus c, same graph shifts c units left side. So here it is plus c, it will shift left, minus c here shift right, whereas c added outside, okay, what happened, plus c it shifts c units up and minus c units down. So shift by up by c units, down by c units, and here minus c means right shift and plus c means left shift will happen. So this is the basic idea for shifting, also known as translation. So let us see this with examples. So the vertical translation, vertical shift, as I told you now, plus c means shifting will happen c units upwards. Okay, so let us see this with examples. Let us see this with example. See, this is the graph of y is equal to x square, and suppose if I want y is equal to x square plus 2, what happens? See, the graph, same graph is shifted c units up, I mean 2 units upwards. Okay, I just written that red color change, but graph is same graph shift 2 units upwards when it is plus 2. Okay, so that is vertical translation. Suppose if it is fx minus c, and remember c should be positive, so what happens? Same y is equal to x square, let us consider. Okay, and suppose if I do y is equal to x square minus 1, what happens? 1 unit down it will shift, translation will happen. So we can combinedly write all this for vertical translation. See what happens. This blue one is your y is equal to x square, okay, and this red one is your y is equal to x square, maybe plus 1 you can write, and this green one is y is equal to x square minus 1. This is about vertical translation. Now let us understand horizontal. This is horizontal translation. See, when c is added to the argument, plus c means shifting will happen left side. This is horizontal shift left side. Okay, c should be positive, please remember. So y is equal to fx, left by c units you are going to shift. Okay, let us try to understand this with example. This is your y is equal to x square. Okay, so let us see this example. So this is y is equal to x plus 1 whole square. See, x plus 1 whole square means it will pass through 1. Instead of passing through origin, it will pass through 1. 1 unit left side it will shift when it is plus 1, x plus 1 whole square. Okay, that is in place of x, you are putting x plus 1. That is what happens. Okay, same story when it is x minus c, shifting will happen c units but right side. Right shift will happen. So let us take the same example. Y is equal to x square and y is equal to x minus 1 whole square. It is x minus 1 whole square. 1 unit right side it will shift when it is x minus 1 whole square. Please remember this. So this is about horizontal translation. Okay, we can combinedly write the entire story. See, this blue one is your y is equal to x square. See, this green one is y is equal to, see, when it is shifting left means it is actually x plus 1 whole square, and it is shifting right means it is x minus 1 whole square. So this point would be 1, this is 0 and this is minus 1. See, same graph will not change, sir, only the shift will happen to that many units. Is it clear? Like that. So this is about your horizontal translation and previous one is vertical translation. Clear? Now let us understand the next two types of transformations, stretching and compression. Okay, suppose your function y is equal to fx is something like this. This is your y is equal to fx function. Okay, now what happens? if you multiply this fx with c outside, c into fx, so the c into fx will be equivalent to stretching. So the graph would be something like this. This is c into fx, c into fx, that is stretch will happen. Whereas, okay, of course here c should be greater than 1, sir, that you should remember. And suppose if you divide fx by c, that is 1 by c into fx, what happens? It would be vertically compressed. See here, c into fx is vertical stretch, fx by c, that is 1 by c into fx, is vertical compression. Okay, this is stretch, and the now 1 by c into fx, this is 1 by c into fx, is vertical compression. Okay, so that is the idea. Now what I do is I take one more diagram to express horizontal one. Now suppose this is your graph. Okay, that is your fx, sir. This is your fx. Now for horizontal one, when you do c, that is f of cx, that is when argument is multiplied with c, the compression will happen. The compression will happen. So the graph would be compressed if it is multiplied with. The graph will be compressed. Okay. Whereas if you do f of 1 by c times x, the graph will be stretched. Okay. Horizontal stretch will happen for f of 1 by c into x. Of course, c should be greater than 1. So please remember, c, when c is multiplied outside, fx multiplied with c, vertical stretch will happen. When you divide, vertical compression will happen. See, the process will be reversed for horizontal. When you multiply with c, compression will happen. Divide by c, stretch will happen. That variation always will be there for vertical and horizontal. So this is the story about stretch and compression. Let us try to understand with this same story with example. Okay, let us see the examples for this. So the vertical stretch, as I told you, when you multiply with c into fx, c should be greater than 1. What happened? Vertically by, it is stretched vertically by a factor c. Let us understand with example. So now look here, this is blue one is your sin x graph, y is equal to sin x graph, and the red one is your sin x multiplied with 3 sin x. So at x equal to pi by 2, sin x is 1, but x equal to pi by 2, this 3 sin x is 3. This is 3 and this is 1. So stretching is happened vertically by a factor 3. 3 units factor stretch is happening. Okay, you can see one more example. Okay, this one is e power x. This blue one is e power x, whereas the red one is your e power 3x. Sorry, not e power 3x, 3 into e power x. 3 into e power x. So actually, you know, at x equal to 0, e power x is 1, but x equal to 0, 3 e power 3x is 3. Vertical stretch is happening. So we can also understand vertical compression. We have to divide by c for that. Let us see that. This is vertical compression. 1 by c times fx, where c greater than 1. Compression, shrink, will happen vertically by a factor of c. Okay, so let us understand this with example. Now blue one is your sin x, and the black one is your sin x by 3. This black one is your sin x 1 by 3 times sin x. 1 by 3 times sin x. Okay, same example for e power x also you can take. The blue one is your e power x, and the black one is your, okay, 1 by 3 times e power x. Okay, vertical compression is gonna happen. Vertical compression is gonna happen. See, compressed. Vertically it is compressed. The graph is compressed vertically. See here also, see, the sin x is original one. Okay, and 1 by 3 times sin x is vertically compressed by a factor of 1 by 3. So at x equal to pi by 2, sin x is 1. This would be 1 by 3 sin. This would be 1 by 3, and this would be 1, like that. So that is about vertical, okay, stretch and compression. So we can combinedly write the entire story, sir, to understand that entire story. This is sin x, this is sin x. So what is the red one? The red one is 3 sin x. And what is the black one? The black one is 1 by 3 sin x. So 3 sin x is vertical stretch, 1 by 3 sin x is vertical compression. Same thing we can write for e power x also. The blue one is e power x. The red one is 3 into e power x. And the black one is 1 by 3 times e power x. So 3 into e power x is stretched by 3 units because it is 1, sir, it is 3, and if you see this is 1 by 3. Compressed by factor 1 by 3, like that. So this is about vertical stretch and vertical compression. Okay, now we try to see the horizontal one. Horizontal stretch. See, for horizontal, what happens when you divide by c, stretch will happen. And when you multiply with, of course, argument, when you divide argument by c, stretch will happen. Multiply with c, compression will happen. Okay, so that is the idea. So let us try to understand the same story with an example. Now look here. Now the blue one is our sin x, favorite sin x graph. This is sin x. Now what happened? You divide it by, say, 2. Okay, you divide this graph, this black one, sorry. The black one is your sin x by 2. Sin x by 2. So what happens? See what happened? A horizontal stretch is happening. See, actually it is 0 to pi. What should happen? That is happening for 0 to 2 pi it is happening. It is stretched by a factor 2. It is stretched by a factor 2. When you divide argument by 2, it is stretched by a factor 2. So that is what going to happen. Okay, same thing we can also see for e power x, sir. Same story for e power x. See, this is original e power x and this is e power x by 2. Stretched by a factor of 2. Stretched by a factor of 2. Okay, and now we can see the compression. When you multiply argument with c, compression will happen. When you multiply argument with c, compression will happen. Horizontal compression. Of course, c should be greater than 1. So let us see, understand this with example. So the blue one is your original sin x. Blue one is your original sin x, whereas the red one is, okay, sin 2x. Sin 2x. So what happens? See, compression is happening. Actually, blue one is taking 0 to pi. It is just we are having one loop. Whereas for 0 to pi, this red one is completed the entire period. So compression happened by a factor 2. Compression happened by a factor 2. Same thing we can understand even for e power x also, sir. So the blue one is your regular. Blue one is your regular e power x. Whereas the red one is e power 2x. So we can combinedly write the entire story, my dear friends. Okay. So there will be a lot of confusion here. So please be careful. The blue one is your sin x, original sin x. Okay. The blue one is your sin x. Okay. Next, black one. Where is the black one? See, black one is stretch is happening. So it is actually black one is sin x by 2. Stretch will happen when you divide by 2. And the red one is sin 2x. Compression is happening. See, when you multiply argument with 2, compression. When you divide argument by 2, stretch will happen. Of course, the same story we can write it for e power x also. This is your e power x. And the black one is your e power x by 2. And the red one is your e power 2x. Okay. So e power x by 2 is when you divide by 2, argument divide by 2, stretch will happen. Multiply argument with 2, compression will happen. Horizontal compression. So this is about your vertical stretch and compression and horizontal stretch and compression. Is the idea clear? Now the reflection, y is equal to minus fx. Suppose your y is equal to fx is your original graph, and when you do minus fx, then it is reflection about the x-axis. Suppose your y is equal to fx is this graph, okay, and when it is minus fx, this would be reflection about x-axis. And same thing, f of minus x is there, then it is reflection about y-axis. This would be f of minus x. That is reflection about y-axis. Okay, so this is about reflection, sir. Very simple one. So minus fx means reflection about x-axis. Okay, f of minus x, that is argument is multiplied with minus sign, then it is reflection about y-axis. Okay, so let us try to understand with examples. Yeah, so this is your y is equal to e power x graph, and this one is minus e power x graph. Minus e power x graph is this. It is reflection about x-axis. Okay, minus e power x, because same values, e power x values, minus of the values means you go to the negative direction. Okay, that is it. Now same thing, f of minus x means reflection about y-axis. Reflection about y-axis. You can take the example for this also. Yeah, so this is y is equal to e power x, and this is y is equal to e power minus x. The red one is y is equal to e power minus x graph. So this is about it. So it is y is equal to e power x, and this is y is equal to e power minus x. And suppose if it is y is equal to minus e power x, this would be the graph of y is equal to minus e power x. Okay, so minus fx means reflection about x-axis. Reflection about x-axis. F of minus x means reflection about y-axis. Please remember. So these are the basic properties. Now we try to take up examples. Okay, now start with this particular example, my dear friend. A very simple example. X square minus 6x plus 10. We need to draw the graph of this particular function. What we need to do is we make a perfect square out of it. X square minus 6x plus 10 is there, no? You make it perfect square. X square minus 6x is there, no? A square minus 2ab plus b square. So if it is 2ab, 2 into 3x. So 3 square should be there. So you just made 3 square, add 3 square and subtract 3 square. This plus 10 is anyhow there. So this fellow is nothing but x minus 3 whole square. This is minus 9 plus 10 is plus 1. So this is your function. Okay, this original function x square minus 6x plus 10 can be written as x minus 3 whole square plus 1. Okay, now let us see how to draw this particular graph using our operations. Am I clear? So first of all, y is equal to x square. Y is equal to x square means 1, 2 means it should be somewhere 4. So graph is something like this. This is y is equal to x square graph. But here we need to get this x minus 3 whole square. So first of all, what is x minus 3 whole square? So when you subtract 3 from the argument, minus 3 means shift is happened 3 units right side. So this x minus 3 whole square would be 3 units. Instead of passing through 0, 1, 2, 3, it passes through this. So the same graph which you are going to get is like this. Let me draw this somewhere here. So the same graph you are going to get like this. It shifts 3 units right. X minus 3 whole square graph is this blue one. Okay, let me write it with blue. X minus 3 whole square. Then what is that you want? X minus 3 whole square plus 1. See, for this graph plus 1 is added. See, plus 1 means what, sir? Fx plus 1. 1 unit up, you need to shift it. So the same graph will be shifted 1 unit up. The same graph will be shifted 1 unit up. So this would be the graph of x minus 3 whole square plus 1. So from x square graph, I could able to get the graph of this x square minus 6x plus 10, which is same as x minus 3 whole square plus 1. Is the idea clear? So this is how we can get new graphs by making some transformation from old graph. 1 minus sin x graph. Okay, it's a dangerous one. Okay, because if you are having the problem with drawing, it's obviously danger one. See, concept is very simple, but only thing is you have to be very careful while drawing. Okay, that would be only difficulty. So let us try to understand. This red fellow is your sin x actually. Now what is minus sin x, sir? Minus fx means reflection about x axis. So let us use different colors so that we'll better understand. So minus sin x is reflection about x axis. So you are going to reflect it. So this fellow, like, so this is minus sin x. The black one is your minus sin x. So minus sin x is ready, but you want 1 minus sin x. 1 minus sin x means minus sin x plus 1. So let us use some other color. What is that I want? Minus sin x plus 1. What is it, sir? Whatever minus sin x is there, you shift it 1 unit up. So the same graph you have to shift 1 unit up. That is very difficult. So it shifts 1 unit up. You have to draw the same graph by shifting 1 unit up. Something like this. Okay. So same black one, we shift 1 unit upwards. So here it is 0, it goes here like that. So this is your 1 minus sin. So when you know basic graphs, you can get other graphs using this simple shifting, okay, reflection properties and other things. Clear? The next interesting graph is mod fx graph. Graph of mod fx. So what we need to do is, whatever the portion of the graph below the x-axis, we need to shift it to the above x-axis. That is the basic idea for this. For example, this is graph of sin x. The red one is sin x graph. Sin x graph. And if you want mod sin x, what is the graph of mod sin x? So whatever part is below the x-axis, we need to remove this part and we need to shift it to the above x-axis. Like this. So the black one which I am drawing is your mod sin x graph. So above x-axis you keep it as it is, below x-axis you just transform it to the above x-axis. Like that. Continue. So this fellow would be your mod sin x. Okay, one more example. For example, you all know log x graph. What is log x graph? It is like this. Now you want to know mod log x. You want to know mod log x. I'll write here. There is no space here. I'll write mod log x. What is mod log x? So this part above x-axis you keep it as it is. The part which is below x-axis you have to shift it to the above x-axis. So this part need to be reflected about x-axis. So it goes something like this. So this would be mod log x. The part which is below x-axis just need to be reflected about x-axis. That means to be reflected about x-axis. Transform about the x-axis. That is about mod fx. Okay. Let us see one more. Now let us try to understand the graph of f of mod x. F of mod x. I try to explain with this e power x graph. So e power x graph, we all know it. So this is the graph of e power x. So what we need to do is, for this graph of f of mod x, means I want to know the graph of e power mod x now. So what I need to do is, retain the graph which is to the right side, positive side of x-axis. That is, this part you remove. From here, whatever graph is there, you keep it as it is. So remove this part. Left side part you remove. That is, only to the right side of y-axis portion you keep it. Now what happened? Whatever right side part of y-axis, The graph is there, you reflect it about y-axis. You just reflect this graph about y-axis. So this would be the graph of e power mod x. Same thing, you have to remove the part on the left side of y-axis. Okay, left side of y-axis, I mean y-axis is there, no, left side part you remove it. Whatever right side part is there, just reflect it about y-axis. That would be the graph of e power mod x. So these are the graphs of some very basic functions, and we also learned the concepts of shifting, that is translation, compression and stretch, reflection, and this mod fx and f mod x graphs also. This would be sufficient for our engineering mathematics. So this is about the review of graphs of basic functions and the new functions from old functions. Okay, is the idea clear? Thank you.